Hello and welcome. Today we're looking at electrophilic aromatic substitution reaction, and we're going to be looking at a simple aromatic compound, benzene. So when you look at benzene, you have a number of hydrogens. If we focus on this hydrogen, for example, it can be substituted with an electrophile and you end up with that product. So that proton has been substituted with an electrophile. So in this example, the electrophile is a nitronium ion. That's a nitronium ion electrophile, and that's generated in situ by reaction between nitric acid and sulfuric acid, and then the end result is that that proton will be substituted with NO2. So that reaction is called nitration. Next, we look at a reaction that's called sulfonation, where the hydrogen has now been substituted with SO3H, and the electrophile in this case is generated by using sulfur trioxide and sulfuric acid. So when you react those two together, you form the electrophile, which then substitutes the proton. In this example, we see that the proton has been substituted with a bromine, and that's because you form what's called a bromonium ion intermediate by the reaction between bromine and iron tribromide, FeBr3, and that reaction is called bromination. In this reaction, the proton has been substituted with a chlorine here, and that's because you form a chloronium ion intermediate by the reaction between chlorine and iron trichloride. That reaction is called chlorination. Here is another example where now this proton has been substituted or replaced by iodine, and that's because you form an iodonium ion intermediate when you react iodine with copper chloride, that's copper 2 chloride, and that reaction is called iodination. Another reaction is where we use alkyl halide here with aluminum trichloride catalyst, and in this case you end up forming carbocation intermediate, so you lose that bromine and therefore you form a plus charge on that carbon, and that will actually be a primary carbon, and you end up substituting that hydrogen with the alkyl group. But the problem is that because you form a primary carbocation, that can rearrange and move the positive charge to that carbon, and therefore you end up with a mixture of this product and the other one where now it's connected to that carbon, because this goes through a secondary carbocation that's more stable. This reaction is called Friedel-Crafts Alkylation, which requires the alkyl halide and aluminum trichloride catalyst. A related reaction to that is called Friedel-Crafts Acylation. And the reason for that is because the substitution occurs at the acyl position. So this is acyl halide, and you need aluminum trichloride catalyst. So in this case, you generate the acylium ion, plus, remember the oxygen still has lone pair of electrons, and you can actually draw resonance where these electrons will move there to form a triple bond, and because of that, that carbon is fixed as an electrophile. You do not have any rearrangement as in the case with alkylation. So this is a very good reaction because they are able to do the substitution at that particular position without any rearrangement. So in this case, that proton will be substituted with the acyl group, and you end up with that acyl group connected to that position. Thank you very much for your time. If you enjoyed this video, please press a like and also subscribe to support the channel.